Okay, good day to each and every one of you who are currently watching this video, a video presentation all about the shear and bending moment diagrams. We have here a given cantilever beam, a length of 12 feet, an applied load of 1,000 pounds here at point A, and a uniformly varying load equivalent to 360 pounds per foot at the whole beam. Okay. We have here the support at the wall, directly at the wall, and obviously since this is a cantilever beam, there should be a bending moment generated here at the support B, okay, at the wall. And our goal for this problem is to determine what would be the corresponding shear and bending moment diagrams, and of course not only that, but to also determine what would be the corresponding forces inside our beam having an external load of 360 pound per foot and this 1,000 pound concentrated load or applied load here at point A. Okay, so before doing that, let's try to simplify first the free body diagram of this beam. So we have here 1,000 pounds at this point. Okay, we have here 1,000 pounds. This we have the bending reaction force bending M. Let's say this is sub B. And uniformly varying load. But before that, we need to look for the concentrated load of this 360 pound per foot. So are we going to do that? You just need to apply the area of the right triangle. Since the geometrical shape of our uniformly varying load is a right triangle, we can just simply use the area of the right triangle. This is the area method. So looking for P sub C, that should be 1/2. The base is the whole length of the beam, which is 12 feet, multiplied by the height, or rather the magnitude of the load that is being imposed onto the beam. So 360 pound per foot, cancel the unit foot, and the remaining unit should be in pounds. So P sub C is equivalent to approximately, that should be 2,160 pounds. Okay, 2,160 pounds. Okay, this is the equivalent concentrated load here. So somewhere this should be 2,160 pounds. And the next step here is to determine the distance of this 2,160 pounds from point A or here at point B. So how are we going to do that? All you need to do is to use the centroidal formula for a right triangle. Since this is the right triangle, it goes like this. And this one, let's assume that is P sub C, or the concentrated load. This portion of the right triangle is 2/3 of the length, and this one is 1/3 of the length. Means to say, if the whole length is 12, means to say this one is 2/3, so that should be 8 feet, and this one should be 12 divided by 3 is 4, so that should be 1/3. Okay. And after doing this, we can now somewhat find 4M sub B. And not only that, we also have this reaction going upward. Let's say this is R sub B. Because this is a cantilever load, we have an applied load going downwards, means to say that this wall here is also reacting upward, because that is the only thing that is supporting our beam here. So R sub B is going up, and then obviously this bending moment B is also rotating counterclockwise, and that is just our initial assumption. So the next step is to solve for M sub B. So how are we going to do that? All you need to do is to use the summation of moments at point B so that we can eliminate this R sub B. So rotating counterclockwise is positive. The summation of forces at B is equals to 0. So we have this M sub B, which is positive. That's our initial assumption. We have this 2,160 pounds. So the rotation is counterclockwise, so that should be positive. 2,160 pounds multiplied by the perpendicular distance equivalent to 4, okay, 4 feet. And we have this 1,000 pounds rotating clockwise, so that should be negative 1,000 pounds multiplied by 12, because that is the perpendicular distance. Solving for M sub B, transposing everything, to the other side and then rearranging. That should be 1,000 pounds positive multiplied by 12 minus 2,160 pounds multiplied by the perpendicular distance, which is 4 feet. Don't forget about the feet here. So M sub B, the answer for that one should be approximately 3,360 pounds. 3,360 pounds, pound-foot. And since we have this positive answer, means to say that our initial assumption for this bending moment here at B is correct. So this one is 3,360 pound-foot. Okay? And if you want to solve for R sub B, you can just simply use the summation of forces. Okay, so summation of forces going up is positive along the y-axis. So that should be 1,000 minus 2,160. And basically that's it. Minus a plus R sub B. Solving for R sub B. So R sub B is equals to 2,160 minus 1,000. And then the reaction at B, that should be 1,160 pounds going upward. Since we have this positive answer, means to say that our initial assumption was correct. So this one is equivalent to 1,160 pounds. Since we managed to solve for the reactions here at point B, we can now proceed on the next step. So how are we going to do that? Well, I'm just going to free this space here so that we can continue. So don't forget, our first step here was to solve for the reactions. And the next one is to use the method of sections. Okay, so now we managed to find for these two. The next step here is to either use the left-right section of the beam. So this is the portion of the beam where I managed to do the sectioning. I'm going to consider the left side. Okay, so upon doing that, consolidating the left side of this beam, okay, this is the free body diagram going like this. This is the section 1-1. We have here the shear load going downward and the bending moment. Let's say this is C, so M sub C, V sub C. And we have this external load, 1,000 pounds. Okay, 1,000 pounds and the intensity. This is the new intensity. Okay, and of course this is distance x. Don't forget about that because we don't know what is the definite distance or the definite length of this beam that we managed to do the sectioning. And okay, the thing here is that since we managed to do the sectioning of this entire beam and we only have 2 points A to B, means to say that the whole beam is continuous. If we consolidate or consider the left side only, means to say that we will have a new intensity here, W or omega. And in order for us to determine what would be the new intensity, we're going to use the Ration proportion. So if this is the whole uniformly distributed load, okay, this one is 360 pound per foot and the whole length is 12. So what is this? That would be the new intensity, and this length is x. Okay, so this one is x. And our goal here is to solve for the new intensity omega. That should be opposite over the adjacent, it's tangent, right? So 360 divided by 12 is equals to intensity omega over x. Solving for omega, that should be 360 divided by 12 x. So the new intensity should be, you just need to divide that. 360 divided by 12 is 30x. So that should be our new intensity here because we did the sectioning. This one is 30x. Okay. Upon doing that, for us to use again the equilibrium forces, we must look first the corresponding concentrated load of this 30x. Okay, so let's go back to our free body diagram. Let's do this step by step. if this is the new intensity, okay, this one is omega is equals to 30x, and don't forget that this one is 2/3 of the base or length, and this one is 1/3 of the base or the length. Okay, applying again the area for the right triangle, A is equals to 1/2 base multiplied by the height. Replacing everything, this one, let's assume this is P sub C. So P sub C is equals to 0.5 multiplied by the base, which is x, and then the intensity, 30x. So simplifying, that should be P sub C, so 30 multiplied by 0.5 or divided by 2, that should be 15. X multiplied by x, that should be 15x squared. Okay, this is the new concentrated load of this uniformly varying load. So let's assume this is here, P sub C is equals to 15x squared. So I'm going to free this space again so that we can have to work on. Okay, now the next step here is to write again the simple free body diagram of this beam. This one is V, this one is M sub C. You can assume what point here that where we did the sectioning. This one is 1000, and this one is the concentrated load, 15x squared. So we all know that this one is 2/3. Okay, this one is 2/3x, and this one is 1/3 of x. So solving for V, that should be the summation of forces going upward is positive or downward if you want. So F sub y along the y-axis, that should be 1000. And we have this concentrated load minus 15x squared minus V. Solving for V, that should be negative 15x squared plus 1000 pounds. So the unit for the shear load is in pounds, so let's retain, okay, let's put the unit here. And the next step is for us to solve the reaction bending moment C by summation of moments positive counterclockwise at this section, point C equals to 0. Just need to do this. We have, of course, M sub C positive. This 1000 is rotating clockwise, so that should be negative 1000 multiplied by the perpendicular distance, which is x. Okay, x, and then this one, 15x squared, is rotating counterclockwise, so that should be positive 15x squared, and the perpendicular distance is 1/3 of this whole length, so 1/3 of x. 1/3 of x. And the next is to simplify, so M sub C is equals to just going to simplify this first, 15/3. Okay, so 15/3 x cube, okay, because x squared times x is x cube. 15/3 minus 1000 of x, and the unit is pounds per foot. So we managed to solve for the shear formula and the bending moment formula for this section, and let's continue that on part 2.